This 11th lecture we shall consider one of the alternative form of Fourier series, that is the complex Fourier series. Earlier we have stated that if we have a function f of x which satisfying Dirichlet's condition in AB, then we can expand it in trigonometric Fourier series as f of x is equal to a0 by 2 plus summation over n is equal to 1 to infinity n cos of alpha n x plus bn sine of alpha n x, where alpha is equal to 2 pi by delta, with delta is equal to b minus a as usual. This series involves two semi-infinite sums. So this is one way, this is trigonometric Fourier series involving two semi-infinite sums. Semi-infinite means n tends to 1 to infinity. That's why semi, 1 infinity sums. Instead of two semi-infinite sums, the series could be written in terms of a single double infinite sum, in which case the n ranges from minus infinity to plus infinity, and the zero value accounts this term. That would be the one of the alternative form of Fourier series known as complex Fourier series. We start with the Euler expression that e to the power I plus minus x is equal to cos x plus minus I sin x, which leads to cos of x is equal to 1 upon 2 e to the power ix plus e to the power minus ix, and sine of x is equal to 1 upon 2i e to the power ix minus e to the power minus ix. These are known as the Euler's expressions. If we use this, then this term with the help of these Euler expressions becomes f of x is equal to a0 by 2 plus, the 2 will be common, so we take 2 out, and we will have summation over n is equal to 1 to infinity for we will have an e to the power I alpha n x plus e to the power minus I alpha n x. This is for cos, plus if we take this out, this can be written as minus I by 2 e to the power ix minus e to the power minus ix. So if we write it in this fashion, 2 is taken common, bn, and then it is e to the power plus I alpha n x minus e to the power minus I alpha n x. Then we collect the coefficient of this, and we rewrite this as This is the coefficient of e to the power I alpha n x, and then we write you see that these two terms we can get from this term, we can get this from this by changing n by minus n. So we write it as summation over n is n tends to minus infinity to n tends to plus infinity Cn e to the power I alpha n x, where the coefficient c is defined in this fashion. Cn is equal to half for n greater than 1. This is equal to A0 for n is equal to, it is n greater than 0. It is A0, and for if we write c of minus 5, then it would involve a of minus 5, b and b of minus 5. But in trigonometric Fourier series, there is no minus subscript of an and bn. So to avoid this, we have written in this fashion. A better way of writing is to put the modular sign. So this can be written as this is a better way of writing these things. So this is known as complex Fourier series. And it involves a single double infinite sum. This is the change. So how do we define partial sum? In trigonometric Fourier series, we define partial sum when small n ranges from 1 to capital N. And here we define the partial sum as summation over n is equal to minus n to plus n Cn e to the power I alpha n x. So there is altogether 2n plus 1 number of terms, which is same as here. Now the thing is to find out the expansion coefficients. Earlier we have found that the Euler expression for determination of the Fourier coefficient were different for A0, An and Bn. Here we will have a single expression, and let me check how to find it out. So we start with the fact that this is only of use. So we write f of x is equal to summation over n from minus infinity to plus infinity Cn e to the power I alpha n x, with alpha is equal to 2 pi by delta, and Cn, for Cn we have this definition, twice Cn is equal to a And how to find out the expansion coefficient? To find out the expansion coefficient, we multiply both the sides of complex Fourier series by e to the power minus alpha nx. So we multiply f of x with e to the power minus I alpha mx and integrate the result or dx from a to b. And on the right hand side we will have summation over Cn, and n tends to then we will have e to the power I alpha n minus mx dx from a to b. If we write it, we will have summation over n Cn integration of cos of alpha n minus m plus I sine alpha n minus mx dx. Note that since alpha is this factor is actually 2 pi n minus m delta x. So we know this is I c n minus m, which is equal to delta times this is equal to delta times delta and minus m, nm, and this is equal to I s n minus m0 identically. So we will get it as this result now becomes C summation over n Cn delta times delta n m. This is delta times Cn. So the formula for determination of Cm is Cm is 1 by delta, so there is no 2 as we found in the case of trigonometric series. For alpha we write 2 m by x by delta f of x dx from a to b. This is the Euler formula for the determination of Fourier coefficient. Let me apply this to a function which we have already done. We have done in the case of trigonometric Fourier series. So we know that for trigonometric Fourier series, f of x is equal to x when defined between minus c to plus c. We will have an is a0 and an are 0, a0 and an are 0 since it is odd, and bn is 2c by n pi minus 1 to the power n plus 1. Now we calculate Cn. In this case delta, so it is 1 upon delta f of x e to the power minus I 2 n pi x by delta dx, and from it is a to b, so this becomes 1 by 2c for delta. Then we will have x e to the power minus delta is equal to 2c minus, we take this is first function and this is second function, so we will have 1 upon 2c is there. When we integrate this, we get c by minus I n pi minus I n pi, and then we will have x e to the power minus I n pi x c minus now first thing is that the coefficient c cancels out. When we take this I to the numerator, it will be plus I, so we will have I by 2 n pi. This is the simplification of this part, and then this will be c times e to the power I n pi, because x is equal to c, minus and this is plus c to the power plus I n pi. This is the first term, contribution of this term, and if we here we will have you see that this is sine. This is sine n pi and it is 0, and this much is 2c. This is equal to 2c cos of n pi. So this result is I upon 2n pi times 2c cos of n pi. Cos of n pi means minus 1 to the power n. This is Cn, and we know that now we compare it with the relation of Cn with Bn. You see that Cn is equal to in this case Cn, if we use this definition, Cn is equal to minus I by 2 Bn, and we know that Bn minus I by 2, Bn is 2c by n pi minus 1 to the power n. So 2 cancels out, so this minus we take over there, so it is Ic by n pi, which is Bn there were minus 1 to the power n plus 1, so it is this. I have written it Bn, yes, Bn n plus 1, so n plus 1 plus, so and these two are the same. So we have now we come to the other properties of complex Fourier series. We have learned that in trigonometric Fourier series that if the function is even and is defined in a symmetric interval, then Bn is 0, and if the function is odd, then if the function is odd, then a0 and an are 0. Let me see how the property is reflected in the case of complex Fourier series. In that case, we first write Cn 1 by delta, which is equal to 2c for if a is equal to minus c and b is equal to plus c and delta is equal to 2c, then Cn is equal to 1 upon delta integration a to v f of x e to the power minus I alpha, and x dx with alpha is equal to 2 pi by delta. 2 pi by delta is equal to pi by c. So this for symmetric interval becomes 1 upon 2c minus c to plus c f of x e to the power minus I n pi x c dx. We now change x by minus x. Then what happens? We replace x by minus u. So this becomes plus c, this is minus c, f of minus u e to the power I 2 n pi u by c, because x is replaced by minus u, so the sign is plus, then d of minus u. So here from a minus sign will come, and we will adjust it again as 1 upon 2c f of minus u e to the power plus I n pi u c du minus c to plus c. From this we have gone to there by introducing u is equal to minus c. So that the changes are there, and then there is a minus sign, we replace d of minus u by du, and this minus sign has been adjusted in adjusting the limits of the definite integral. Now, if f of x is even, then f of minus u is equal to f of u. Then we will have Cn even 1 upon 2c minus c to plus c f of u e to the power plus I n pi u c du. This is Ce of minus n. Ce of minus n. So Ce of n is Ce of minus n for even, and we see what happens. Ce of n is equal to Ce of minus n. Here Ce is half That is to say, they are real, because Bn part is 0, it is real. And if fx is odd, we have f of minus u is equal to minus f of u, in which case Cn of odd is equal to Cn of odd. Now we apply the condition that half a of n minus I b of n is equal to minus half a of n plus I. This gives you a of is equal to 0. This means that all the an is 0, this is purely imaginary. So the in trigonometric Fourier series for even function, Bn is 0, and for complex Fourier series, Cn is real, purely real. On the other hand, for odd function in trigonometric Fourier series, only Bn survives, and in the case of complex series, Cn's are purely imaginary. If the function do not have any parity, in that case Cn is a complex. In the earlier example that we have considered belongs to this category, and we found that Cn is imaginary. The last point that I am going to address is what would be the Parseval's formula for complex Fourier series. Earlier we have found the Parseval's formula, Parseval's theorem for a trigonometric Fourier series, and here how would be its corresponding form. Now we are to integrate f modulus square dx between limits a to b. So we write it as a to b f star of x, f of x dx. For star we use the dummy variable m, and for this is dummy variable n. So there will be two sums, m sum from minus infinity to plus infinity, and n sum from minus infinity to plus infinity. Cm star Cn, and then integration e to the power I to n minus m pi x delta dx integrated from a to b. So this term, as we have shown in the earlier occasion, that it is delta times delta mn. So we will have m sum, n sum, Cm star Cn delta times delta mn. So this is delta times one sum will goes Cn modulus square, or the average value of the square of the function in the case of trigonometric Fourier series, the result was so the Parseval's formula for complex Fourier series is this. Now this stands, as we have stated, that it stands for the completeness of the expansion. If we know the function on the left hand side, and we can calculate the left hand side of the value, left hand side. Now if we take sufficient number of terms, actually this cannot be possible to take from n is equal to minus infinity to plus infinity. So in reality one takes this as n is equal to minus n to plus n Cn modulus square, and by increasing the value of capital N, we will find that the right hand side is very near to left hand side, so that the difference between left hand side and right hand side can be made smaller than some accuracy level. Then we said that the complete number of terms has been included. As the accuracy level is increased, the value of capital N will increase. Another thing, very soon we shall start complex Fourier transform, in which case we shall see that this is our starting point. We shall start Fourier transform from this, that is the Parseval's formula for a complex Fourier series.